All right, now that we've completed Chapter 6, I'd like to take you through a review process. And like I've mentioned on previous videos, one of the difficult things about not being in a classroom and having to do this on your own is, you don't get a chance for the teacher to stress what's important on the test, what's not important. And so I'm going to do the same thing I've done on previous ones, and that is I'm going to take you through this review and set it up for you just like it'll be on the exam. So I don't want there to be any surprises. So the topics that I'm going to cover on this review are what I'm indicating are important, and these are the things you should be looking for when you're preparing for your exam. So the first thing we did in Chapter 6 was we looked at the idea of slope as a rate of change. We looked at average rate of change and instantaneous rate of change. If you recall, the average rate of change is the slope of the secant line, whereas the instantaneous rate of change is the slope of the tangent line, or the derivative. So what you're going to have to do on your exam will be a question like this one here, where you have to show me that you understand the concept of rate of change, average and instantaneous. So the question says, in a certain memory experiment, a person is able to memorize m words after t minutes where the following function applies. M of t equals, and then you see the function there. So what we're saying is that a person will memorize the number of words that they can memorize will be given by the function m at any moment in time t, where t is in minutes. So the first question says, find the average rate of change of memory between 10 and 20 minutes. So average rate of change is slope of the secant. So the average rate of change, so we could just say rate of change average is equal to, now all you're doing here is finding slope. You're finding the slope of the secant line. So what we want to do here is the slope of a secant line is it's just going to be delta m, the change in the memory, over the delta t, the change in the time. This is not a calculus concept. This is simply an average concept or a slope of a secant line. So what we want to do now is we want to calculate these quantities. So delta m is going to be the change in m between 10 and 20 minutes. So this is going to be m at 20 minutes minus m at 10 minutes. That'll be what's happened to the memory, the number of words between 10 and 20 minutes. And then we're going to divide that by delta t, which is the change in time, which will just be 20 subtract 10. So you'll notice that we're just using the slope formula. It's simply the slope of a secant line. So what you want to do is you want to plug the number 20 into your memory function. Now I've already done that, and hoping I did my calculations correctly here, but I got 32. So that would mean that the person had memorized 32 words after 20 minutes. Then we want to subtract how many words they had memorized after 10 minutes, which turns out to be 9. And then we want to divide that by the change in time, which is 10. So if we do that, we end up with 23 over 10, or about 2.3. And the units here are very important. I always look for units on a test. They tell me that you understand what you've actually found. It's a rate of change. It's number of words memorized per unit time. So this would be words per minute. So what we've actually found is that between the 10 and 20th minute, the person is averaging an increase of memorizing 2.3 words every minute. It doesn't tell us how many words that they were learning at any particular moment in time. It just gives us the average between 10 minutes and 20 minutes. Now the next question says, find the rate of change at 10 minutes. Now this question is asking us to find the slope of the tangent line at 10. We want to know the slope of this function exactly at 10 minutes. And of course, that is a derivative concept. So what we would do here is we would just find m prime at t. So using our power rules, the negative 1 over 1,000 is just a constant. So that would just stay out front. Negative 1 over 1,000 times the derivative of t cubed, which is 3t squared, plus the 1/10 is a constant, times the derivative of t squared, which is 2t. Now, if you want, you can combine these numbers, or we can do that in a second here, but the question wants us to find the rate of change at 10 minutes. So we are looking for m prime at 10. So it's going to be negative 1,000 times, and then we're going to plug 10 into here, so 10 squared is 100, so this will be 300 plus 1 over 10 times 20, which will give us, zeros can divide out here, so we'll end up with negative 3 over 10 plus 2, which will turn out to be negative 0.3, so this will be 1.7 words per minute. And again, just to stress that you understand what we found here, this is the average rate of change between the two times. This is the rate of change precisely at 10 minutes. So 10 minutes into the experiment, the person is memorizing an additional 1.7 words per minute. That would be their rate of change. Next, we looked at the concept of velocity and acceleration. If you recall that velocity is a rate of change, this is really just a continuation of the last section. Velocity is a rate of change, so if you want the average velocity, it would be the secant slope of the position function, whereas the instantaneous velocity would be the derivative of the position function. And then, of course, acceleration is just the rate of change of velocity. So by differentiating the function a second time, we get the acceleration function. So in this example, you may recall we spent some time looking at questions where you had a particle moving along a straight line. So this particle is moving along the x-axis, and its position is being described by a function of time. So we're given the formula there. S is the position of the object in meters, and t is the time in seconds. So the first question says, find the velocity and the acceleration at time t. So what we're being asked to do there is simply find the velocity and acceleration functions. Now, I've already said it, but we know that velocity is just, the instantaneous velocity is just the derivative of position, the rate of change. So the velocity function v of t is just the derivative of the position function. So it's just s prime at t. So we simply need to use our power rules and differentiate our position function. So we would get 3t squared minus 30t plus 63. That function right there will give us the velocity of this particle at any moment in time. Now the question also asks us to find the acceleration at any moment in time. Well, the acceleration function, a of t, is just the derivative of the velocity function. It's just v prime of t, or if you like, it's the second derivative of the position function. So we differentiate one more time, and we get 6t minus 30. This is the power of derivatives, is that by simply differentiating those two functions, we can now describe the position, the velocity, and the acceleration of that particle at any moment in time. The next question is simply asking us to be more specific. It is saying what's the velocity and the acceleration right at 2 seconds. So we want the velocity at 2, which would just be, so we're going to use our velocity function. So 3 times 2 squared minus 30 times 2 plus 63. So 2 squared is 4 times 3 is 12, and this will be plus 3. So 12 plus 3 would be 15. And again, units are very important. Please make sure you include your units on the test. So the units would be meters per second. That would be the instantaneous velocity of the particle at 2 seconds. To find the acceleration at 2 seconds, we just have to recognize that we want the acceleration function. So we want a at 2, which would be 6 times 2 minus 30, or 12 subtract 30, or minus 18. And the units would be meters per second per second. So meters per second squared. So the 15 meters per second tells us that the object was moving with a positive velocity, and at 2 seconds it happened to be moving with a negative acceleration. The next two questions are just a little bit more thought-provoking. The question C says, what's the position of the particle when its velocity is 36 meters per second? The purpose of that question is I just want you to think about, you have three functions available to you. You have a position function, a velocity function, and an acceleration function. So you have to ask yourself, what does the question want me to do? It wants me to find the position. It wants me to find the position of the particle. So I obviously have to use the position function. But in order to solve the position function, you need to know the time. And the question doesn't tell us that. It tells us that the velocity is 36 meters per second. So we obviously have to use the velocity function. And what we're going to do is we're going to use the velocity function, and we're going to solve for time. So what we're going to do is we're going to say the velocity is 36, and the velocity will equal, so that's our v value, and then it's going to equal the function 3t squared minus 30t plus 63. Now we have a quadratic equation, so we need to solve for time. So we need to make it equal to 0. So 3t squared minus 30t. We need to subtract the 36, which will give us 27. And now this is equal to 0. And now we need to factor. One factor of 3, so we can take the 3 out, and because it's a constant, we can divide by 3. So 0 equals t squared minus 10t plus 9, which we will then factor. And we get t minus 9 and t minus 1. So what that's telling us is that there were actually two different times when the velocity was 36 meters per second. There was a time at 9 seconds and the time at 1 second. Now the question wants us to find the position. This just gives us at what times the velocity was 36 meters per second. So now we have to find s at 1 and s at 9. So s at 1, I'm just going to plug 1 into my position function. 1 is always a nice number to work with because this will just be 1 cubed, which is 1, 1 plus 63, which is 64, and 64 minus 15, which would be 49. And the units would be meters. So the object was 49 meters to the right of the origin when it was traveling at 36 meters per second. Now the other one, 9, isn't quite as simple. We're going to have to plug that in and we're going to get 9 cubed minus 15 times 9 squared plus 63 times 9. Now, unfortunately, I didn't do this calculation in advance. So 9 cubed is 729 minus 15 times 9 squared, which would be 1215, plus 63 times 9, which would be 567. So 567 plus 729 minus 1215, and we get 81 meters. So the object was traveling at 36 meters per second at 2 different times, and therefore 2 different locations. And the last question, at what times is the particle at rest? Again, just trying to get you to think about what that means. If a particle is at rest, then it has no velocity. Its velocity is 0. So you're going to want to pick the appropriate function. The appropriate function would be our velocity function. So we would say velocity 0 is equal to 3t squared minus 30t plus 63. Now the rest of this is just similar to solving this equation, except we're going to divide by 3 again. So we're going to get t squared minus 10t plus 21. And this is going to factor into t minus 3 and t minus 7. And so the particle is at rest at 3 seconds, and it's at rest at 7 seconds. You can see how through the analysis of these 3 functions, we can pretty much tell everything we want to know about the particle, which is the power of differential calculus. Okay, next we looked at the word problem section of applications of calculus, and the first major category of problems we studied were called optimization problems. Optimization problems are where you're looking for the optimum solution to a given situation, that being either a maximum or a minimum. The topic was broken into types of word problems. I'm going to test you on just 2 types of problems, so concentrate on these 2 types. The first one would be what I call number problems, where there doesn't seem to be any real importance to the question other than it's just meant to get you used to the whole concept of trying to find an optimum solution. So the first number question we'll look at here says find 2 positive numbers with a product of 200 such that the sum of one of the numbers and twice the second number is as small as possible. So when you're doing an optimization problem, in this case, you don't really need a diagram. So what you want to do is identify what's changing in the question. What are your variables? Well, you're looking for 2 positive numbers. So we could say, let x equal a number. And then we're looking for another number. Now, you could do this one of 2 ways. I'll use 2 variables to show you how this is done using 2. Some of you may skip the step with 2 variables and just immediately go into 1. Depends how well you understand the question. But I'm looking for 2 numbers. One of them is I've called x. Now the other number for, let's just say now we haven't read further into the question, so we'll just say let y equal another number. So we're looking for 2 numbers. The 2 numbers could be just any 2 numbers with a product of 200. So we've identified them as being x and y. Now your next job is to identify what is it you're trying to optimize. Well, in this case, you're trying to find the smallest sum possible. So we could call that S. So we're trying to minimize the sum S. So what we need to do now is write a function that gives us the sum of this in this particular question. So our sum, what is it we're trying to sum? It says the sum of one number, so the sum of x, and twice the second number. So our sum is going to be the first number plus 2 times the second number, y. Now when you're doing an optimization problem, you cannot have 2 variables on the right-hand side of the equation. You have to have a function of 1 variable. And that's why I chose to use 2 variables here. So you could see that in these questions there's always a link between the 2 variables. Something is linking the x and y here. When I select a number for x, I just can't arbitrarily select a second number for y. Something is linking these numbers together. And what's linking them together is that they have to have a product of 200. So I know that the first number x multiplied by the second number y has to be 200. Therefore, y, the second number, would just be 200 divided by x. Now, it would be perfectly fine on an exam. Instead of saying let y equal the other number, you might have just immediately saw the connection that their product was 200, and you might have just said let the second number be 200 over x, and that's perfectly fine. I chose to do this, I guess, the long way, just so you can see that if you ever have 2 variables on one side, you need to find a relationship between them that will eliminate one of the variables. So what I can now do, excuse me, is I can now write the sum as a function of 1 variable. The sum is x plus 2 times y, which is 200 over x. And you're going to want to simplify your function before you differentiate it. So I'm going to write the sum is x plus 400 x to the minus 1. You're always better off moving that x to the numerator because the 400 is a constant. There's no point using a quotient rule when you simply have a constant times a function. Now, when you're doing optimization problems, you must set your restrictions. You must identify what the restrictions on x are. In this case, x is a positive number, so it has to be greater than 0, and the product has to be 200. So, imagine what you could let x equal. You could let x be, x could be 1, and the other number could be 200. But you could also make x very large. You could make x, 2,000. If x was 2,000, all you would have to do is compensate with the other number by making it small enough to give you your product you want. So it would be 1 over 10. You could let x be a really small number. X could be 1 over 1,000. And then you could compensate by making the other number very large. In this case, it would be 20,000. As long as their product is 200, we're allowed to let x be one of the numbers. Now, obviously, x could never be 0 because 0 times another number would never give you 200. It'll always give you 0. So our restrictions are going to be x is going to approach 0 but not quite reach it. And of course, in theory, x could approach infinity. We could, in theory, make x infinitely large. We would just have to compensate by making y infinitely small. Whenever you have round brackets on your restrictions, you can ignore them because what that means is if you actually went to these restrictions, if you actually approach 0 or approach infinity, your sum would become infinitely large. You'd be adding up a very large number to another really small number, but still the overall impact would be a very large number. We're looking for the smallest sum possible. So basically, when you have round brackets, you can disregard those endpoints. Now we are simply going to apply our strategy for finding extreme. We know that the extreme values are either at the endpoints, which we can disregard, or any critical points being where the derivative is 0 or the derivative is undefined. So we're going to take the derivative. We're going to take ds dx. That's why we have to have a function of one variable, because we're differentiating with respect to that variable. So our derivative would be 1, and then this is a constant, so it would just be minus 400 times x to the minus 2, which I like to put back on the bottom because I'm going to have to solve. I'm now going to make my derivative equal to 0. Critical points are wherever the derivative is 0 or undefined. So I'm going to solve this equation. So 1 equals 400 over x squared. Cross multiplying and taking the square root, we get x equals plus or minus 20. Now we can disregard the 20 since we can't have the negative 20 since we can't have a negative value. So that means that our x, one of our numbers would be 20. The other number y, the other number would be 200 divided by 20, or 10. So the question wanted us to find two positive numbers. So the numbers are 20 and 10. Now the question didn't ask us for the maximum sum, so we don't have to actually find that, but we just need to identify the two numbers. We're going to look at one more category of optimization problems. This category is area. In this case, a lifeguard wants to rope off a rectangular swimming area in the water, and they have 400 meters of rope to do this with. They're going to use the shoreline as one of the sides of the rectangle. And the question is, what should the dimensions be of the swimming area in order to maximize its area? So here's a question where I think a picture is kind of handy. So what we have here is, let's say this is the shoreline right here. What the lifeguard wants to do is they want to rope off a rectangular swimming area. So they want to rope off something like this, and they have 400 meters of rope in which to do it. Now they obviously don't need rope for the shoreline, so what we need to do is assign our variables. So what could you change in roping off this area? Well, obviously you could change the width of the area, of the swimming area, and also its length. So let's say I call this X. That would obviously be the same as this, and we'll call this Y. So there's our picture. You either need to have a picture identifying your variables or some kind of let statement. You need to identify what are the quantities that are changing in the question. So in this case, it would be X and Y. I don't require you to have a let statement if you've got a properly labeled diagram like that. Now, what is it we want to do? We want to maximize the area. So we want to maximize the area. We'll call it A. So your next job then is to write a function. We need a function that gives us the area of that rectangular swimming area. So the area would equal, well, in this case, it's just a rectangle. So area of a rectangle is length times width. So our area would be X times Y. Once again, we have two variables. So you have to ask yourself the question, what's linking the two variables together? Well, the lifeguard only has 400 meters of fencing or rope at their disposal. So the 400 meters of rope is going to make up these pieces right here, these three pieces. So this X and this X, or 2X plus this Y, would have to add up to the 400 meters of rope. This is going to be the key to unlocking the puzzle of how to get rid of one of these variables. So we can isolate the X, or the Y, sorry. We can say Y is equal to 400 minus 2X. And now we can replace the Y in our area function with its equivalent expression of X. So we can say that the area is equal to X times 400 minus 2X. And we now have a function of one variable. We have area as a function of X, which would equal 400X minus 2X squared. Our restrictions, again, this has to be a rectangle. So imagine what could the person do with this shoreline? Well, in theory, what you could do is you could have a really long, narrow, rectangular swimming area. So you could make this X here and this X here approach 0. You couldn't actually make them equal to 0 because then you wouldn't have any a rectangular area at all. You just have one long piece of rope along the shoreline. So in this case, our X, once again, could approach 0, but not quite 0. But going the other way, this time X can't go to infinity. We only have 400 meters of fencing, so of rope. So imagine that the lifeguard chose to make the area like this. Imagine this piece right here getting smaller and smaller, the length here. As that gets smaller, these two pieces are going to get longer. Imagine that you did make this 0. Well, these two pieces right here would be 200 each because you only have 400 meters of rope. So your upper restriction in this case is 200. But once again, because they are round brackets, we don't need to analyze them. They would give us the minimum area. If you actually did approach 0 or 200, this area would become really small because even though it would be lengthy, it's a product and you'd have a really small other value. I do insist though that you have these restrictions. Make sure you include them on the test. So now we take the derivative, a prime, which would be 400 minus 4x. We know that the maximum or minimum values will occur at critical points, so we make our derivative equal to 0, and we get 400 equals 4x, or x is 100. Now the question asks for the dimensions. Excuse me. When it asks for dimensions, that's referring to the length and the width. So again, you could write a word sentence. Even a picture here, a picture is just fine. The dimensions, well, we've discovered that this should be 100. This should be 100, the units being meters. And the y value, you can find the y value from this relationship right here, or just common sense. There's 400 meters of rope. We've used up 200 of it, so this would be 200 meters right here. And that's the maximum area that the lifeguard can create. You might think that it would be a square if we were using all four sides, but because we're only using three, it ends up being a rectangle in which the length is twice as long as the width. Okay, finally in Chapter 6, we looked at the other major category of word problems in calculus. They're called related rate problems. Related rate problems are questions where things are changing with time, as opposed to an optimization problem where you're just trying to find the best solution to a given situation. Here you have things that are moving with time. So the first thing we need to do is identify our variables. Sometimes a picture is necessary. In this case, it's a triangle. The picture itself isn't really that important in this case. Whether you draw the picture or not is not really essential. But what is essential is that you identify what's changing in the diagram. It says the area of a triangle is increasing. So obviously we're referring to the triangle's area. And the area is increasing at a rate. When you see that phrase increasing at a rate, you know you have a derivative. And so if we call A the area, so if we let the area be A, then we know that dA dt is 4. The dA dt being the rate of change of area with time. You can always tell by your unit. Centimeters squared per minute is the area unit over time. The base is increasing, so the base being, let's say, B, the bottom here. So B is the base. The base is also increasing, so dB dt. When you're doing a related rate problem, it's always differentiating with respect to time. And this would be 1. So you'll always be given some rates of change, sometimes 1, sometimes 2, but you'll be given some derivatives. Then, of course, there's the derivative you're trying to find. The question goes on to say, at what rate is the altitude of the triangle changing? Well, the altitude is its height, so we can say h is the altitude. So the question wants us to find dH dt, and then you're usually going to be given a particular moment when you want to find that. You're looking for dH dt when the altitude is 20, when h is 20, and when the area is 80. So there's your setup. You want to identify any variable that's changing and then write them as derivatives. Some of them are given, some of them are being the goal of the question. Now you need a function that you can differentiate with respect to time. In the case of area, it's usually a known formula. The formula for area of a triangle is 1/2 base times height. Now I picked this question because often you have more than one variable, and the question is, do you need to get rid of them? Do you need to get rid of one of the variables? Well, the key is what you have up here. This sort of sets the problem up for you. In this question, we need a dA dt, a dB dt, and a dH dt. So we need all three variables in this formula. So what you do at this moment is you simply differentiate every term with respect to time. So this is where we have to use implicit differentiation. So I want to differentiate A. If I differentiated A with respect to A, it would just be 1. So I would have 1, but then I have to use the chain rule and put my compensating term dA dt. In other words, it's just dA dt. The 1/2 is a constant and can be removed. And then you have to recognize that base times height is a product. So not only do we have to use implicit differentiation, we also have to use our product rule. So the derivative of b would be 1 if we took it with respect to b, but we're not. We're taking it with respect to time. So we have to put dB dt times h because of the product rule, and then take the derivative of h, which would be dH dt times b. And of course there would be a 1 here as well, but you don't need to write that. The derivative of h is just 1. So there is your differentiated function. Now at this point you want to do an analysis and just ask yourself, do I have what I need? I need to find dH dt. Well, it's right there, so that's a good thing. But in order to find dH dt, you need to know all the other missing quantities in your function. So you need to know dA dt, which we know. You need to know dB dt, which you know. And you need to know the height and the base. And of course, the question wasn't that obvious. It didn't give you the height and the base. It only gave you the height and the area. But of course, you have a function that describes area as a function of base and height. So the area, 80, is equal to 1/2 the base, which we don't know, times the height, which is 20. So 1/2 of 20 is 10, divide by 10, and it turns out that the base is 8 at the moment we're solving this problem. All of the hard work is done now. The rest of it is just plugging in numbers. So this is 4 equals 1/2 times dB dt, which is 1, times the base, which is 8, plus dH dt, which we're trying to find, times the base. Sorry, I guess I made a mistake back here. This should have been 20. That was the height. My apologies. This is the base. This is h. So b and h. Now we have to solve for dH dt. We could distribute the 1/2 into the bracket, but it's probably just as easy to multiply both. If you do that, you'll just get 8 equals 20 plus 8 dH dt. Subtract the 20, we get minus 12 equals 8 dH dt. And then divide both sides by 8, and we get our answer. The height is changing with time at a rate of -12 over 8, or -3 over 2 centimeters per minute. In other words, the height was actually decreasing with time at that particular moment. I'm going to do one more example of a related rate problem. This time it's from the category on volume, and I've selected a question involving a cone because of the replacement of a variable that needs to occur. So what we have here is sand being dumped onto the ground at a rate of 1.2 meters cubed per minute. And the sand is forming a cone. So what's happening is the sand is being dumped on the ground, and it's falling into a shape of a cone. The variables that are changing, when you have a cone, there's 3 things that are changing here. Obviously, the volume V is changing. And the other 2 quantities that are involved in a cone are its height, h, and the radius, r. As more sand falls onto the pile, the height of the cone is going to increase, and so is the radius. So our variables are going to be radius for, I'll use the variable r for radius, and the variable h for height. Again, on an exam, you don't need to necessarily write down your variable statement if you have a diagram that indicates what your variables are. So I would accept that. Now your derivatives, sand is being dumped on the ground at a rate. So there's our derivative, and it's a volume. We know that by the units, meters cubed per minute. So the volume is increasing, dV dt, at a rate of 1.2 meters cubed per minute. So that's our given rate of change. We're being asked to find how fast is the height of the pile growing. So the question wants us to find dH dt, and the moment it wants us to solve it is when the pile is 3 meters high, so when h is 3. So that would be our setup. 3 quantities are changing. One of them is given to us, and one of them is unknown. Now we need a formula. The formula for the volume of a cone is a known formula. You do not need to memorize these formulas. If they're required for the test, they'll be provided. The formula for volume of a cone is 1/3 pi r squared h. Now the reason why I've selected this question is because of what happens next. The only derivatives that are important to us in this question are dv dt and dh dt. Nowhere in the question is the letter r being used. So if we were to differentiate the formula in its given form, we would end up with a dr dt, and we can't have that. So there has to be some kind of relationship between radius and height, and the question tells us that. It says as the sand piles up in a cone, the base diameter, the distance across the base of the cone, is always equal to the height. So the height is always equal to the diameter. But the diameter, of course, is just 2 radii. So this is what's important in this question, is we know that the height is always equivalent to 2 times the radius. So the radius will always be 1/2 of the height. And that's the key, because we can now take that statement and we can substitute it in here for radius. And we can now come up with a formula for volume of a cone as a function of height only. So we're going to have 1/3 pi times 1/2 the height squared times the height. This function here is volume as a function of height only, which is what we need because when we differentiate, we only want to have a dh dt and a dv dt. Now before you differentiate, in its current form, this would be very awkward to take the derivative of. We'd have to use a power of a function rule. We would have a product rule. So you definitely want to simplify this. So what we would do is if we square this 1/2, it'll become 1/4. 1/4 times 1/3 will be 1/12. And the pi is a constant. So we'll just end up with pi over 12 out front as a constant. The h squared times the h will be h cubed. We've now expressed our function, volume, as a function of height only in its simplest form. We can now take the derivative. So we differentiate this function, and because it's a related rate problem, we're taking the derivative with respect to time. So we would write dv dt, the derivative of v being 1, times the compensating term dv dt. The pi over 12 is a constant, so you would just leave the constant out front. You would then take the derivative of h cubed, which is 3h squared, but that would be with respect to height. Remember, when you're doing these related rate problems, you're always taking the derivative with respect to time. So we have to multiply by our compensating term, which is dh dt. You see why we had to get rid of the r. Every time you take the derivative of a variable, you're always going to have that variable expressed as a rate of change with respect to time. And we didn't want to have a dr dt in this question. The rest of it now is just number plugging. We have everything we need to know. We know that dv dt is 1.2. Now 1.2, just so you know, like I'm going to do this without a calculator. 1.2 is really just 12 over 10, which I can reduce to 6 over 5. So I'm going to replace this with 6 over 5 equals pi over 12 times 3 times 3 squared dh dt. And the reason why I'm doing this as a fraction, not a decimal, is I just want to show you that a person doesn't really need a calculator for these. Most of these questions work out quite nicely. To get this dh dt by itself, all I have to do is get rid of this constant in front of it. So everything that's being divided gets multiplied, and everything that's being multiplied gets divided. I can first of all reduce. This 3 will go into this 12 4 times. And so I can now go dh dt equals, I've got my original 6/5, and then this 4 that's on the bottom is we're dividing by 4. We would have to multiply by 4 to get rid of that. And on the top we have pi times 9, or just 9 pi. And so that 9 pi would get divided. We can reduce the 6/9, we can divide by 3 and get 2/3. And you see how nicely this works out. We just end up with 8 over 15 pi. And our units there, it's height with time, so it would be meters per minute. Now again, I've said that if you want to change this to a decimal, if you're not comfortable doing this arithmetic here, if you wanted to leave everything in decimal form and just find an approximate answer, If you want to just, divide 8 by 15 pi and get an approximate answer, that's perfectly acceptable. I'm not going to deduct marks on a test if you decide to do that. I just thought I'd show you how simple it is to work in the exact form. So that wraps up our chapter 6. And so good luck with your exam, and I'll be getting ready to do some more videos here for chapter 7.